Okay, section 10.3 or worksheet 10.3. Today we're going to kind of learn the basic rules to help us to decide if something a series converges or diverges. For the beginning, we're going to deal with only positive term series. Okay, so we're going to make sure all of our terms are positive, no negative terms in them at all, because negative terms, adding a positive with a negative, kind of throws a little wrench in things in terms of approaching a number. So we're going to stick with positive term series for now. Second half of the chapter will introduce you to what happens with negative terms. Last section, you had some problems where you had to actually figure out what something added up to. Most of the time, we can't do that. Only nice little series work in such a way that we can actually figure out what they add up to. However, we can figure out whether they add up to something or not. We might not be able to figure out what it is, but we can figure out if it converges or diverges. So from here on out, no one's going to ask you to find the sum. We're just going to say, does the series converge or diverge? So the same question is going to be asked the next 100 problems you do in this class, 20 or so a night, however many. I'm making up that number. Sorry, don't panic. This question is going to be the same. It's going to say, does the series converge or diverge? And you have to run a test, a formal test, to determine whether it converges or diverges. Okay? So I'm just going to give you kind of a weird little theorem here and kind of blow past this one fast. But it says if a sub n is a positive term series and there exists a number m such that s sub n equals a sub 1 plus a sub 2 all the way to a sub n is less than m for every n, then the series converges to some less than. This basically just says if I know all the numbers add up to something less than m, then the series will converge to something less than m. Seems a little silly, but it's a theorem we just need in the next test. So it's not a theorem you're ever going to use. I just want to throw it in there to say we're going to use it. The first test, or actually the second, because I guess you've had the nth term test, is called the integral test. Doesn't that sound fun? We're going to do integrals. You can actually integrate a series to determine whether it converges or diverges. Okay, so what we're going to do, here's what it says. Let a sub n be a series. Obtain a function, f of x, by replacing n with x. We're just saying put x's in there instead of n's. It doesn't really matter. And then take the integral from 1 to infinity. So what we're going to do is we're going to take the integral from 1 to infinity. And if that integral equals a number, so remember indefinite integrals from last chapter, or 2 chapters ago, I guess. If that integral from 1 to infinity approaches a number, then the series is going to converge. It's not going to converge to that number. It's actually going to converge to a number less than that. So that's hence that theorem I just gave you. If it equals infinity, then it's going to diverge. Okay, so I have 3 examples here. I'm going to just do one example right now. And then at the end of my lesson, I'm going to go back and do the other 2 examples if you want to see more. That way you can maybe save you some time. But I will do all of them at some point. So basically the idea is here 1 over n. We already know 1 over n diverges. It's the harmonic. We've done it. But now we can prove it with the integral test. So what that means is you take the integral from 1 to infinity of 1 over n. Okay. They say replace it with x. Doesn't really matter. It's just a variable, right? So I'm going to integrate that, which is the natural log of x, from 1 to infinity. I know I should be doing limits, right? We replace that infinity with a limit, but I'm going to kind of shortcut it a little bit. It's the natural log of infinity minus the natural log of 1, which is infinity minus 0, which is infinity. Therefore, it diverges. That's the integral test. Pretty simple, pretty straightforward. If that were a number, like 10 or 20, then the series would converge. Just remember, however, it doesn't converge to that number. Okay, that allows us to say that it does actually converge. All right, so I'm going to come back to those last 2 at the end if you want to see more. Right now, I'm going to kind of move along. One thing to notice about this test, this is not a great test. This test is only useful if you can integrate the thing. You're going to see a lot of series that you go, oh my God, you look at that, I would never want to integrate it. So the integral test is kind of like a last resort. It's a cool test, works pretty nicely, but it's kind of a last resort if you can't integrate it. Okay. P-series, or another term for P-series is hyperharmonic series. A P-series is anything of the form 1 over n to a power. So I just did 1 over n. If you go back, I just did 1 over n. You can see the next example I'm going to do is actually 1 over n squared. Okay. These are called P-series. Anything that looks like the number on top means nothing. It doesn't have to be 1. Remember, it could be 2 or 3 or 4 or 10. It doesn't really matter because you're just going to factor it out anyway. P must be greater than 0, however, because if P is less than 0 or a negative number, that would flip it up to the top. It would change everything. And now it would just be n to a power, which means the terms would be getting bigger and bigger and bigger, which means it's not going to converge anyway. Normally, I would do a proof of this in class, but I'm just going to tell you, okay, rather than a proof. Maybe we'll do a quick little proof in class next time we see each other. So the basic idea is very simple. A P-series will converge if P is greater than 1. And it will diverge if P is less than or equal to 1. Plain and simple. Now, we don't get a lot of P-series. However, the next 2 tests I'm going to give you are called comparison tests. So we're going to compare things to things we already know. So what we're trying to do is develop like a library of series that we already know, whether they converge or diverge, and then use that. Here's the way I think about this. It's kind of weird. You're going to see me do this one later, but we already know that 1 over n diverges. I'm going to show you later on that 1 over n squared actually converges. I've mentioned this before. It's just a P-series, right? You can see it right now. It's a P-series with P greater than 1, so it's going to converge, right? Here's the way I think about it. Both of these graphs look like that. Okay, they just get smaller and smaller and smaller, and the terms approach 0. Don't forget the terms approach 0. However, the purple one, which would be this one, notice it's a little bit below the other one, right? Because it's 1 over n squared. It's going to be a smaller number than 1 over n. So the way I think about this is the purple one is approaching the axis, the x-axis, faster, meaning it's getting smaller faster. So we need something to get smaller faster to be able to converge. If it gets smaller slowly, then it's going to add up to infinity. But if it gets there fast, it's going to converge. It's kind of my thought process. So like 1 over n to the 1/2 is smaller, right? That's above here, which means it's going to diverge. You don't have to really know why, I guess, but that's kind of the theory behind that. Is it's got to be getting to the x-axis fast enough. The numbers have to be getting smaller for sure, but they have to be getting smaller fast enough. Otherwise, we're still going to add up to infinity. So what we're going to do is we're going to use these P-series in the next 2 tests. Next test is called a basic comparison test. Basic comparison test says we got 2 series, and if one of the series converges, so in this case, if B sub n converges, but I also know if the other series is smaller than that series for every term, then that other series has to converge also. So think about this. Let me draw you a little picture here. I got some series B sub n that converges, so it's going to converge to some number. Then I come along with this A sub n. So sorry, this was B sub n. Then I come along with this A sub n is always less than B sub n. Then it's going to converge too, because it has to converge to something less than whatever B sub n is converging to. And by the way, it doesn't even have to be for all terms. We write for all terms, but it actually could cross here. It's still going to be true. Those other early numbers aren't going to matter. The numbers after are the ones that matter. And then vice versa. If B sub n diverges, so now I got another series. Let me get rid of the purple one here. Hang on. Or sorry, the red one. So now I still have the same B sub n, but now I know this diverges. If I have another series that's above it, it's got to diverge also because every term is bigger, right? So if the one adds up to infinity, then the other one has to add up to infinity also because it's bigger. The problem is if B sub n diverges, let's say, but A sub n, so let's say this one diverges, and A sub n is less than it, then I don't know anything. So it has to be the right comparison. It's called a basic comparison test. So let me show you how this works. Here's an example. Okay, 3 over the square root, that's the square root, sorry, it looks funny, square root of n minus 1. The minus 1 is not inside the square root. We're going to do what's called a basic comparison test. So what we're going to do is we're going to take this 3 over the square root of n minus 1, and we're going to compare it to something that we already know. So this is where things get a little tricky. It takes a lot of practice, like what should I compare it to? In class, the next couple of days, I'm going to kind of give you ideas of how to look at something like how do you know it's a basic comparison or another test, well, like what you should look for. Right now, we're basically looking for p-series because that's all we know. So notice I can very easily compare this to 3 over root n, okay, which is just a p-series. Okay? So how do I compare it? Well, notice that this denominator is smaller than this denominator, which makes this number bigger than that number, which allows me to do that. I also know, this is how you write this up, by the way. Formal says everything has to be written up to explain to me what you're doing. This is a divergent p-series. P is equal to 1/2, right? So that's a divergent p-series, less than 1, diverges. So now I have something that's greater than a divergent series, which means it has to diverge also. So then I say, therefore, 3 over root n minus 1 diverges. And then I always say the test, right? Because I'm running a test. I haven't said anything. By the basic comparison test. Yeah, I don't have any other examples of that one. So, actually, I have another one. Sorry, there's one more. So I'm going to come back to one more at the end again. Yeah, it's hiding up there. Okay, I'm going to come back to that one more at the end. But that's the basic idea of the basic comparison test. You find a series of comparatives. It's not an easy thing to do. It takes some practice. Usually it's p-series that we're going to convert. So usually we take things out of the denominator, we add things to the denominator, add things to the numerator, make them smaller or bigger. So I'll show you another one also. But you have to do the right comparison, remember, because if it's greater than a convergent series, that tells you nothing. And if it's less than a divergent series, it tells you nothing. So it has to be the right comparison, okay? So I'll come back to that last example at the end in case you want to see another one, but I will do the last test and then we'll be done. I got 3 examples. I'll do the same thing. I'll just do one and then I'll kind of start over. So this is called the limit comparison test. The limit comparison test says if you have 2 series and you take the limit as n approaches infinity of one over the other, okay? It doesn't matter which one's on top, which one's on the bottom. And if you wind up getting a number that's greater than 0, not infinity, okay, C is a real number, okay? So I know infinity is greater than 0, but if you get something, any number that's greater than 0, then the series are going to do the same thing. They're either both going to converge or they're both going to diverge. So if you know what one of them does, you know what the other one does, but you have to find the thing to compare it to again. So I'm going to start with this problem here. 1 over the cube root of n squared plus 1. So I need to compare this to something and then take the limit as n approaches infinity. So the only thing we really have to compare things to are p-series, right? Maybe we have harmonic, we have telescope, and we have geometric. There's a couple other ones, but for the most part, we haven't learned a whole lot. So I see, I don't know if you see it, but I see a 1 over n to the 2/3 in here. I hope you can see that n to the 2/3 because there's n squared and a cube root. So I'm going to compare it to 1 over n to the 2/3. When I do this comparison, I'm going to invert and multiply. So now notice it's a higher power rule. Notice a higher power of n in the top is 1. The higher power of n in the bottom is 1. Therefore, the limit of that is 1, which is greater than 0. And I know that seems really funny. Why would I ever write that? Well, we need to write that because it's important. Because if it's equal to 0, we don't learn anything. That's the thing. If it's equal to 0, we don't learn anything. And then later on, 1 is going to have different meanings in different tests. In this case, it's greater than 0. Then I also have to say what I compared it to. This is a divergent p-series. So since I compared it to a divergent p-series, I can then say, and I got a limit, and remember the whole idea of the limit comparison test is that they're going to do the same thing. So therefore, 1 over the cube root of n squared plus 1 diverges. by the limit comparison test. All right, so I'm going to go back. That's the end of the lesson. I know it was only one example of each. We did the integral test, the basic comparison test, and the root test. So I'm going to, the limit comparison test. So I'm going to go back right now. You can feel free to go if you want and try, but I'm going to go back and do a few more examples of each type, just to kind of help out. But if you want to go now, that's good. And here we go back. So I'm just going to go back in order to the integral test first. Integral of 1 over infinity, 1 over n squared. So 1 over n squared is just you can call it x or n, it doesn't matter, is a power rule, right? N to the negative 2. So negative 1 over n is going to be my antiderivative from 1 to infinity. So that's like negative 1 over infinity minus negative 1 over 1. This is just 0 equals 1. Therefore, it converges. And it converges by the integral test. Again, you have to be able to integrate it. So here's another one, the next one. I see a U sub in that one. By the way, you can do other tests. By the way, the second one is just a P-series, so I wouldn't really have to do that. I'm just showing an example. Here's the a U sub. So U equals negative n squared. Du is negative 2n. So the n is going to cancel. So we're going to go 1 to infinity. I'm going to have a negative 1/2, which I'm just going to put in there. And then it's going to be e to the u, which is negative 1/2 e to the negative n squared from 1 to infinity. I'm going to factor out that negative 1/2, and I'm going to get e to the negative infinity squared minus e to the negative 1. This e to the negative infinity squared is e to the negative infinity. Basically, it's 1 over e. It's just 0. It's getting smaller and smaller and smaller. 0 minus 1 over e, which I guess is 1 over 2e. It's just some number. The whole idea is just a number. If it's a number, it converges by the integral test. The integral test is a hard one to figure out how to use because you got to be able to integrate it. So it takes a little practice. Again, it's not a very common test. It's kind of a last resort. I had another example on a basic comparison test hiding right there. So I'm going to just go down to the bottom and do it so you can see it better. Sorry. Let me rewrite it. I have it here. 1 over 2 plus 5 to the n. All right, so the idea is I got to compare this to something. So my first thought is, hey, let's just compare it to 1 over 5 to the n, because that's a geometric. Notice, geometric, r less than 1, it's 1/5, so it converges. So hopefully, my series is less than that series. If it's not less than, I got a problem. It won't work. I got to try something else. So notice that this denominator is bigger than this denominator, which makes this number smaller than that number, which is the right sign, right? Smaller than a convergent is good. So therefore, 1 over 2 plus 5 to the n converges by the basic comparison test. If we had a greater than sign there, we'd have to just try another series. That's the whole idea, just try another one. And let's go back. Actually, I'm just going to keep writing down here. Here we go. I'm going to do a couple more limit comparison tests to kind of show you. They're all kind of similar. 3n squared plus 5n over 2n cubed plus 2n. So I'm going to take this series, and compare it to something. Series talking to me here. 2n cubed plus 2n. What am I going to compare it to? Well, I'm going to compare it to 1 over n, and I'm going to tell you why.
I didn't get that.
Yeah.
Could you try again?
Yeah. Be quiet.
This is as quiet as it gets.
All right, if I knew how to turn that off, I would.
I'm sorry.
There we go. Sorry about that confusion. All right, I'm going to compare it to 1 over n. Why am I going to compare it to 1 over n? Well, the best use of the limit comparison test is with polynomials. So notice polynomial on the top, polynomial on the bottom, because I can just do higher power rules. Higher power rules are really easy. So watch what happens if I invert and multiply. 3n squared plus 5n over 2n cubed plus 2n times n over 1. Now notice that the higher power on the top is now 3, and the higher power on the bottom is now 3. They're the same, which allows me to just say that limit is 3/2. It's really easy and really simple. And remember, what I'm shooting for here is a number, right? A number greater than 0. So if I picked, watch this, I'm just going to kind of do this in purple. If I put like n squared here, then there would be an n squared here. And now the higher power on the top would be 4, which is bigger than 3. So the answer would be infinity, which is not helpful. It does not tell me anything. Then let me erase. Let's say I pick like 1/2. That'd be 1/2. So now notice the higher power is in the bottom. The higher power is in the bottom. That doesn't help me any either, because then the answer is 0, which doesn't help me in the limit comparison test. Remember, the limit has to be greater than 0. So we need to pick the power that gives me equal powers in the top and the bottom, which means really what I'm looking for, the original problem, a 2 here and a 3 here, it's the difference between those two powers. It's the difference between those two powers always. So when I invert and multiply, it's going to make them the same. Now we just got to write it up. 3/2 is greater than 0. So what did I just learn? Well, I just did a limit comparison test. So I got to say 1 over n is what I compared it to, is a divergent harmonic or p-series, either way, series. So remember, the whole idea of the limit comparison test is the two things are going to do the same. So since this one diverges, therefore 3n squared plus 5n over 2n cubed plus 2n diverges by the limit comparison test. Okay, I'll do one more. It's very similar, and then I'll be done. Oops, no limit yet, sorry. Summation 8n plus root n over 5 plus n squared plus n to the 7/2. So same idea. Notice polynomial, polynomial, sort of polynomial. The fractional exponents aren't really polynomials, but it's still doable. So we're going to take the limit as n approaches infinity. We're going to go 8n plus root n over 5 plus n squared plus n to the 7/2. So here's what I'm looking for. Higher power of n on the bottom is 7/2. Higher power of n on the bottom is 1. 7/2 is 3/2, right? So the difference between 7/2 and 1 is 5/2. So I'm going to compare it to 1 over n to the 5/2. The reason I'm going to compare it is because, watch, when I invert and multiply, my powers in the top and the bottom are going to be the same. In the top, power is 7/2, and the bottom 7/2. So the answer to that is 8. 8 is greater than 0. 1 over n to the 5/2 is a convergent p-series. P is greater than 1, yeah. Therefore, everything has to do the same, right? Whatever the one series does, the other one does. Therefore, the series 8n plus root n over 5 plus n squared plus n to the 7/2 converges by the limit comparison test. We'll do lots more in class. Do the best you can with these for sure. They're a little tricky the first time you see them. Hopefully they'll practice. They'll be good, and we'll go over more in class. And I'll see you in class.